Now let's look at balancing the forces. If you look at the satellite, the main two forces affecting the satellite is the centrifugal force and the centripetal force, and they're shown in red and blue. We have seen the inner force, and now we look at the outward force. We can represent that in terms of vectorial notation. It's going to be m, the second derivative of the vector r, pointing from the center of the Earth to the satellite. Now if we equate the two together, then we get the following. M would cancel with m, and gm is nothing but mu, so we're representing it with mu here, and this what remains. If you take this to the other side, we have an equation of the second order, a second order differential equation. To solve this, it's not easy, so we will need to find solution because we have differentiation, and then we need to represent this in a better coordinate system. So this second order differential equation with 6 unknowns, because we have vector here of x, y, and z, vector of x, y, and z, and these are called the orbital elements, as we're going to see later on. But for now, we can see that the current representation of the differential equation is not that easy, so we need to change the coordinate system. The solution to the difficulty of this differential equation is to change the coordinate system. So in the following two slides, we'll look at what are the existing coordinate systems. In this slide, we see reference coordinate axis. We have on the left-hand side what we call the Earth-centric coordinate system. From the name as it appears, we have the XYZ. It is centered on the center of the Earth, so it's Earth-centered. The X and Y plane are in the equatorial plane. So if this is the equatorial plane, the X and Y, if you look at this diagram, it might look easier. So we have the Sun, and this is the Earth. So we have the Earth at the center of the coordinate system, and the reference plane coincide with the equatorial and the polar axis. If the satellite itself might not be rotating on the XY plane, as you can see here, it could be tilted. This is XYZ, and this is the Earth-centric coordinate system. If you look at the other easier system, which now we refer to as Z node, so this is going to be tilted. We're tilting to match the satellite plane. This is called the satellite coordinate system. Still, the Earth is the center of the coordinate system, and the reference plane is the satellite orbit. So if the satellite is orbiting the Earth like this, we're going to shift X, Y to match the plane. Okay, here it was the equatorial plane, and now we are using the satellite. This is going to make the equations much easier, and this is why this is usually used coordinate system. Now still, the orbit, this is what we have done in the previous slide. We have changed the coordinate system, but still using X, Y, and Z will make the equation still complicated. So we're going to go from using the Cartesian coordinate to using the polar representation. On this new axis, we have X, Y, and this is pointing upwards. We have R naught and phi naught. These are the new variables that's going to help us solve the problem, solve the differential equations. We're not going to go over the details. If you can refer to the book for substituting variables and what have you. But solving the two differential equations lead to 6 constants, which we call the orbital constants, which define the orbit, and 3 laws of orbit, which are Kepler's laws of planetary motion. So we'll spend some time explaining the Kepler's laws, and we'll spend time representing or listing the orbital constants. By the way, Johannes Kepler was a scientist in the 16th century to 17th century, and he is a German astronomer and scientist.